I'm just going to give a couple of minutes introduction. My name is Martin van Krenendonk. I'm now the director of the Centre for the Australian Centre for Astrobiology, which Malcolm founded originally at Macquarie University and then transferred here to University of New South Wales a few years ago. So it's my great honour to be able to introduce Malcolm. And this sort of opening slide shows what Malcolm's been concerned about with most of his life, which is wrinkly old things. And I won't say anything more. I won't say anything more about that. But he has been a pioneer in the study of ancient life, and then how to apply that to thinking about, could there be life elsewhere in the solar system, and in fact elsewhere in the universe. And that, in fact, has been his real calling card. So Malcolm started off in his younger, very haughty days as one of the Three Musketeers, together with a couple of his colleagues from the United States, Bill Schopf and John Hayes. And together, those three really pioneered a new discipline, which was Precambrian paleobiology, meaning looking for signals of life in very ancient rocks. And you have to remember that stromatolites, these features, these wrinkly old features that we looked at previously, these structures and rocks made by thin microbial communities, weren't really recognized or discovered until the 60s or so. And so Malcolm got involved in this very early when very little was known about it. And together with these fellows, they really started to look at eking out signs of life in very ancient rocks and really putting together the early part of the history of life on Earth. And they did that, and Malcolm, I think, followed a very well-known precept about the present is the key to the past by studying modern stromatolites, and this is his book from 1972, I think, on stromatolites. To study stromatolites, living stromatolites, he could then apply that to look at very ancient rocks and try and understand what the structures were in those ancient rocks. And he's published many books and also a number of papers. He's been involved in this most recent one that came out last week in Nature and Science and elsewhere. But really, he's most known probably for his interest and passion for searching for life on Mars. He very early got invited to NASA to start to guide their interests into where to search for life in the solar system, and particularly on Mars. And he's been a passionate proponent for the search for life on Mars, when many would regard this dry and dusty planet as devoid of any interest. And we now know from all the discoveries of flowing water on Mars in the past and in the recent that he was absolutely right, that that's an interesting area to go into. So as I mentioned, he founded the Australian Centre for Astrobiology and had this funky logo, which has now been replaced by this more retro logo in some ways. But through all of that, he's been accompanied by Carol Oliver, who's been a very important part of the Australian Centre for Astrobiology, and particularly focusing on the learning of science and the outreach of science communication. And together they have really forged a really wonderful center that I've had the honor to take over. Malcolm's been involved in teaching at all levels, from postgraduate students right down to high school. And he's been a star on TV and radio. And, but of course, his greatest legacy are the students that he's trained and who are following in his footsteps and are engaged in Precambrian paleobiology in the present. So we have here Abigail Allwood, who's an instrument science team leader on the Mars 2020 rover, who was one of Malcolm's PhD students, who incidentally I first discovered from QUT. And she's now at the Jet Propulsion Laboratory in California for NASA. David Flannery graduated from UNSW a few years ago and is her deputy. So we've got a strong presence in the search for life on Mars. And of course now there's a new batch of curiosity-driven scientists who are the next generation and no doubt going to take their place. Just earlier this year, Malcolm was given the honor of being inducted into the Order of Australia for a significant service to science in the field of astrobiology. Now that has got to be unique in Australian history. I doubt there's any other AM who's recognized for his contributions to astrobiology as an author, an academic, an educator, and most importantly, I think for many here, as a mentor. So congratulations, you old bugger, and well done. And we're really delighted to have you here for giving a talk today. So thank you.
I'm pleased to see such a big audience, and I'm really gratified that there's so much interest in the subject. And as Martin said, I'm fairly new to the subject of Mars exploration. That is, it goes back to 1989, and that's halfway through my career. So let me skip this. You've already heard enough about Mars for the time being. And when I figure this out, I'll... Oops. No, it's okay. It's okay.
Oh, you want to do that first?
Yeah. So obviously I want to acknowledge a number of people along the way, the way that Martin already has. But I won't run through all the names, and there were more people as well who helped me in many ways, and including helping me with the slides I'm going to use tonight. So this is a minimal list, but I want to draw out a couple of stories from this list anyway. And one of the stories is that it goes way back to the beginning, my beginning, at here we go, at the University of Adelaide, in Douglas Mawson's department. Mawson was already dead when I was first there as an undergraduate student, but I was surrounded by his paraphernalia, his wooden sleds that nobody would think of using these days, huge, heavy things. And, but more importantly, from my point of view, his specimens that he'd collected from the Coorong Lagoon in South Australia, where he described living stromatolites, and from Central Australia, where he collected a lot of stromatolites. And I actually worked on his collection alongside another student at the time, Wolfgang Price, under the tutorship of Martin Glasner, who was a wonderful supervisor in many ways. He was a real polymath, Glasner, quite a remarkable man who deserves a lot of credit in many fields, but from Vienna, he had a double degree in law and science, and he was an absolutely formidable man for a young student like myself, and hardly dared enter his office to talk to him. He asked me to work on the specimens that Mawson had collected, and so that's what I did, of course, and he got a scholarship for me. I had nothing to do with it. He got it for me from Consig Rio Tinto, it was called in those days, Rio now. He just forgot to tell me that nearly all the literature was in Russian. So I learned Russian. But don't ask me any questions in Russian. I've forgotten all of it. But it's a story of mentors. And in this list, there are many mentors that I've had. So from there, I went to Yale as a postdoctoral researcher, and I chose as my field area Yellowstone National Park with all its hot springs. And the reason I chose it was purely by accident. In those days, students actually went to libraries, physically, books made of paper. And I was wandering through the stacks one day, and I came across an extraordinary monograph by Walter H. Weed, published in 1889, about the hot springs of Yellowstone National Park, and I was captivated. So my field area for 2 years was Yellowstone National Park and the hot springs and the biology. I learned a lot of microbiology along the way. And that's really where this whole story comes from. I didn't get involved in Mars until David Desmarais invited me to that meeting that Martin mentioned. And I'd never previously given much thought to Mars, but here I am, talking about Mars. So that's the background. So what I'm going to do is just, first of all, give you some basic facts about Mars, but I assume you're mostly Mars enthusiasts anyway, so bear with me if I go over things you already know. And then I want to talk about the oldest convincing evidence of life on Earth. And that's what we have in the Pilbara of Western Australia. And Martin and I and others in this audience, Brett Beddington and Carol Oliver, were there last week. And then the implication of what we've learnt from all of that for searching for life on Mars. And I'll tell you up front, the obvious implication is we're not looking for little green people. Right. So if you've come to hear about little green people, then you're going to be disappointed. Or pyramids or faces or whatever. And I want to end by talking about our conservation efforts for the area in the Pilbara where this extraordinary evidence is found. Except I'm then going to give you the latest news, which Martin has already mentioned as well. And there's the Q&A. So a little bit of background. You all know what this is. You can see where our own insignificant little planet is. And there's Mars, of course. A bit closer, you can see that, as you all know, Mars is considerably smaller than the Earth, and one's blue and the other's reddish. But an extraordinary thing, I think, worth dwelling on for a moment is this is the best image we had of Mars in the 1950s from ground-based telescopes. There was no option other than to use ground-based telescopes in the 1950s, and I know there are astronomers in the audience, so Ray, tell me if I got it wrong. But you can see the icy North Pole of Mars, and you can glimpse the South Pole as well. And, oops, I think that is probably Valles Marineris, which you'll see more clearly in a moment. And people have thought about life on Mars for a very long time, for centuries in fact, but the first scientist to take an interest in the possibility of life on Mars was the Italian Schiaparelli. And here's a German version of Schiaparelli's map with the canals on Mars. The idea was that Mars was drying, and there were little green people there who were digging canals, and they got that right. Mars used to be warm and wet. It's no longer warm and wet, so they were spot on. But we now know from the wonderful imagery of something like now 40 missions to Mars, all robotic, by the way, and all one way, by the way. We've never brought anything back from Mars. Bits of Mars have arrived here, accidentally, as meteorites, but we have never brought anything back except data. And here in this beautiful image of Mars, about 100 kilometres across, I think, with a few impact craters from meteors and dry river valleys. And there was some controversy early on about what the fluid was that formed those dry valleys. It was thought by many people to be liquid CO2 because the average surface temperature of Mars is -60 most of the time. So it could have been liquid CO2, but now there's abundant and convincing evidence that it wasn't CO2, it was indeed water. So water once flowed on the surface of Mars. Mars was warm and wet. That's what we hear all the time. Mars was warm and wet early in its history. And in fact, if we look at this map, which is a map of the whole of Mars made using a gamma ray spectrometer on Mars Odyssey some years ago now, you can see the distribution of hydrogen, or in fact water, on Mars. Lots in the north, as you saw from the earlier images, lots in the south, but even quite a lot around the equatorial regions. And you can see the volcanoes on Mars there as well, and there's Valles Marineris. So there is, in fact, abundant water now on Mars. And why does that matter? Well, all life on Earth at some stage in its life cycle requires liquid water. We only have one example of life in the universe. And the way we look at Mars and anywhere else in the universe, as far as that goes, in searching for life, is to follow the water, as NASA says. I mentioned volcanoes, and here is the Olympus Mons, the largest volcano in the solar system. Interesting for a number of reasons. It's huge to start with. It's 500 kilometres wide, has a 12-kilometre high cliff around it. As I like to say, the people who skydive and jump off cliffs near Wollongong wouldn't live very long if they jumped off one of those cliffs. And why wouldn't they live very long? What's the answer to that? If you leapt off a cliff on Mars, why wouldn't you live for very long? Come on. Come on. I'm used to talking to students, sorry. Somebody want to answer that question?
Not enough. High terminal velocity. Very high terminal velocity.
Very high terminal velocity, yes. A fatal terminal velocity. Yeah. 7 millibars of atmospheric pressure on average, compared to 1,000 millibars here on average. So it'd go straight down, fast. But the interesting thing from the point of view of anybody interested in volcanic heat and hot springs is this volcano as a caldera. A caldera is the collapsed top of a volcano. The volcano grows, and then every now and then, there are many examples on Earth of this, they explode, they blow the top off, and they leave a huge crater. And this huge crater at the top of Olympus Mons has blown several times. It's about 90 kilometres in diameter, and that's about the same size as Yellowstone National Park, where I've worked many times. So this is a beautiful example of what to look for if we're going to not only follow the water, but follow the heat and look for hot springs, which is the theme of this talk, and look for life. There would be no better place to go. However, engineers don't like it particularly because it's very high and there's not much atmosphere to slow you down using a parachute. So they're interested in other places on Mars, as we'll see. The achievements of the rovers on Mars over the years have been quite extraordinary, about 40 or so missions, as I mentioned. This is the latest one. And you can see it's laden with instruments of various sorts, and it's sending us back still now wonderful information. You notice no solar panels. It's powered by a so-called RTG, thermonuclear power plant. Now, one of the Spirit and Opportunity rover missions, the engineers at JPL were doing their 24-hour-a-day watch of the data coming in and working out what to do, and they probably got a bit bored. So they started giving names to the rocks they could see. And why is this interesting? Well, they called a rock Hammersley, another one Jackaroo, Wolf Creek, that frightening crater and top end. Wallaby, doesn't sound very American. Pilbara, and so on. What this illustrates is that, I was going to say even the engineers, but sorry engineers and other engineers, that what it indicates that they were fully aware of using the Pilbara as an analogue for what occurs on Mars. So that one-to-one relationship is critical to developing an exploration model. I've worked as a petroleum exploration consultant for years. There was a time when I did that. And so we talk about exploration models. If you've got a whole planet to look at, it's very expensive to explore for anything. Doesn't matter whether it's oil or whether it's life or former life. You need some way of narrowing down the opportunity. And the way they were narrowing down the opportunity, and the way we, Martin and myself and our colleagues and students, narrow down the opportunity is to study the Pilbara. Now let's have a slightly closer look at Mars for a moment and talk about the water on Mars. What you're seeing there are ice clouds, water ice clouds over Mars, and there's the North Pole. So no surprise, but clear evidence. A big surprise, though, is this. There's a scale at the bottom. The image is about 1,500 metres across. These are little channels coming down from a scarp, or just under a scarp, and seen from the Mars Reconnaissance Orbiter, high-rise camera, very high-resolution camera. And so it can see, the pixel size is only about a metre or so. And what's particularly interesting is that because it's done innumerable orbits, these channels come and go. And not only do they come and go, they finish in delta deposits. A little bit hard to see here, but there's one there. And so something is flowing even now on Mars, despite the minus 60 degrees centigrade average temperature. And the explanation of that is that it's an extremely saline brine that is flowing. Doesn't matter that it's saline, it's water. If there's still liquid water on Mars, and if there ever was life on Mars, my prediction, and the prediction of most microbiologists I would say, is that if there ever was life on Mars, it will still be there. And so if we think about exploration strategies for life on Mars, we have two options. We can go for fossils, or we can go for living microbes. Both are good strategies. There's an intriguing relatively recent observation. This is a map of methane, patches of methane, in the atmosphere of Mars. You see a scale of methane concentrations down there on the bottom right. We have methane in our atmosphere, very low concentrations, but it's there. Where does it come from? You're not going to answer me, so I'll have to answer myself. It comes from hydrothermal activity or volcanic activity, nothing to do with life. And it comes from microbes that are called methanogens. They produce methane as part of their metabolism. So that's intriguing. It doesn't prove that there's life on Mars, but it's intriguing. And in a mission that's already up there now, the carbon isotopic composition and the hydrogen isotopic composition, hydrogen deuterium ratios of that methane are going to be measured. And those measurements may be quite strong evidence that there was an origin in life, in microbes. We mightn't have to wait more than a year to get those results. So let's look at microbial life on Earth. Again, that's our model. We're trying to narrow down our exploration strategy. And the tree of life, as biologists call it, tells us some important stories, but first of all, get it in context. That we're there. All the rest of life is microscopic. That's one of the stories of this tree of life. Nearly all life on Earth is microscopic. And in fact, most of the cells in your body are microbes. Your microbiome, as it's called these days, is just that, micro. You're walking culture vessels for microbes. The few animal cells you have are insignificant. So you're looking at the tree of life and you see those three big groups, bacteria, archaea and eukarya, and they're all almost entirely microbes. All life on Earth, nearly all life on Earth is microscopic, and it always has been. It tells you something else, that branch point down there is called LUCA, last universal common ancestor, and current work suggests that suggests an origin of life that's mesophilic, that is at 60 to 80 degrees centigrade. Used to be interpreted to be hypothermophilic, but currently it's interpreted to be mesophilic. So again, that suggests where to look on Earth for the earliest evidence of life, and it suggests a model for the origin of life. I'll say more about that as well. Now, to put it in the framework of time, this illustration is from Dave Demeray at NASA. In the form of a clock, you see it calibrated in terms of billions of years, from the origin of the Earth at 4.56 billion years ago up until now. And you can see that there were no vertebrates until late in life, about 500 million years ago, the Cambrian, as it's called. This is called the Precambrian, and apart from a few possible exceptions and some very interesting research that's happening here at UNSW right now, as I speak, apart from that, all life in the Precambrian was microscopic. Again, the lesson is we're looking for microscopic life elsewhere in the universe. And this classic image was made by the Smithsonian Institution in Washington, D.C. Many years ago as a result of the work with Bill Schopf and John Hayes and myself at UCLA. So it was based on what we see now in Shark Bay in Western Australia, where we have living stromatolites, which is what the microscopic deposits are called. But interestingly, presciently, in the image, the artist included hot springs. And he did that because there was plenty of evidence at that time, and even more now, of high levels of volcanism during these times, that is more than 3 billion years ago. And so you see this relationship between hot springs and marine environments. And that's exactly what we have in the Pilbara. So those are the lessons that I've been emphasising in the last few minutes. And besides the Pilbara, we're very fortunate in Australia of having the best studied and the best conserved example of living microbial mat structures, stromatolites. And they're in this place called Hamlin Pool in Shark Bay in Western Australia, halfway out Western Australia. There are people here who've worked on those stromatolites, Brenda Boone and Tony Larkham in particular, and others. And they come from here, Hamlin Pool. That's about 90 kilometres from there to there. It's hypersaline because of the arid environment. But again, microbes don't mind a little salt, and so they flourish. But it tends to keep the animals out. The animals would otherwise be grazing on the microbial mats and destroying or at least drastically altering them. And so it's a great place to study how stromatolites form. Oops. And in former days, that was me. And that's what the stromatolites in the subtidal realm of Shark Bay look like. They're real reefs. It's entirely appropriate to call them reefs. If you ran into them with your tinny, you'd sink. That's the definition of a reef. It's true. It's true. It's a wonder I didn't drown, but anyway, I didn't. But it's only the upper few millimetres of those stromatolitic structures that are actually alive in the sense that they're photosynthesizing. You see the green pigments. They're photosynthetic pigments of the cyanobacteria. They used to be called blue-green algae, but they're cyanobacteria. And you see the sand grains that get washed onto those cyanobacterial mats during high tides and storms. When that happens, the light is blocked out, and so the microbes either move or grow up through the sand, and layer by layer they build up those big structures I showed. And those cyanobacteria look like this. All those scale bars are 10 microns. Some of them are filaments, some of them are unicellular, some of them are spiral. Some people actually eat spirulina. You're welcome. Where does that lead to? It leads us back to the Pilbara. So we now know that there are stromatolites in the Pilbara. And in this crude map of many years ago, the stars indicate, there's a scale, 100 kilometres, the stars indicate where stromatolites and other fossils were known at that time. And I'm going to look at those in more detail. Some of those fossils come from, not the stromatolites so much, but microfossils, cellularly preserved microbes, come from fossil black smokers, like these modern so-called high-temperature springs black smokers on the sea floor. But most come from calderas, like the caldera of Yellowstone that I've spoken about before. This is White Island in the Bay of Plenty in New Zealand. It's about 5 kilometres in maximum dimension. So it's about the same size, actually, as the calderas that have recently been mapped by Martin's students and Martin himself in the Pilbara. So it's a very good way to visualise what the Pilbara looked like 3.5 billion years ago. And even when you get close up like this, and you're walking around in the caldera, and you don't stay very long because people are being killed in this caldera. It erupts without significant warning every now and then. But even at this scale, you can't see any life. This is what the early Earth would have looked like, would have looked exactly like that. Though the colours would have been different. But if you get close up, and there's a pen in the bottom right for scale, you see the green pigments of photosynthetic algae. These are actually eukaryotic algae. And you see the slimy iron oxidizing bacteria with Fe2O3 or FeOH2 in them to make them brown. And you see what we call native sulfur that's common in hydrothermal systems. This is what we would have found in the Pilbara had we been there 3.5 billion years ago. But there are also marine deposits, somewhat younger, a mere 100 million years younger, that's 3.4 billion years old, that have been studied by Martin and by Abigail Allwood, mentioned by Martin now at JPL. And In the field, if you're looking at a natural slice, vertical slice through a formerly flat layer, they're conical structures. And if you look down on the top, you can see that they're rounded or elliptical. And they built up something that can truly be called a reef. It goes from a rocky shoreline down to deeper water. And so there was marine life that looked like that at 3.4 billion years ago in the Pilbara. But we're going to concentrate on that. Oh, sorry, this is what they look like close up. That's about 30 centimetres across, a natural vertical section again. But if you go back to the old ones, 3.49 billion years old, and these are really well dated. We can talk about that later if you want to know more about the dating. And you can see conical laminae, and there are in fact ripple marks in there and sediments that formed at the same time. So we know that these are, well, we have a strong reason for considering that these are biogenic structures at 3.49 billion years ago. And at other places, many years ago, Schopf and a guy called Stanoramic from UC Santa Barbara and I described fossil microbes, actually cellularly preserved and seen in an optical microscope. There's a SCOBAR 10 microns. Never been able to be duplicated, this work, unfortunately, so in that sense it's not convincing science. But similar microfossils are now known to be quite common in other rocks in the Pilbara. And a lot of this work is that of Bill Schopf at UCLA in recent times. You see filaments and unicellular structures and so on. So the Pilbara, we can now say, has the oldest convincing evidence of life on Earth. Convincing is the key word. There are rocks in the Barberton mountain land in South Africa, up near the border with Zimbabwe, that are the same age, or close to, as those in the Pilbara. And there are some stromatolites there, but predominantly that's volcanic succession. It has nowhere near the richness of record that the Pilbara does. Not to say that it's not important, but the Pilbara is the go-to place to study earliest life. So what does that mean for Mars? Well, geological maps are the starting point. How am I going for time?
You're all right.
I'm okay?
It's 7:05.
Okay. Geological maps are the starting point for any exploration. Martin is responsible for our most beautiful geological map of the North Pole area in Western Australia. This is a geological map of Mars where the pixel size is about 10 kilometres. And you can see that already we know the geology of Mars in considerable detail, despite never having been there. There's nothing unusual about that in one sense, because this is the way geologists start any exploration program for petroleum or minerals on Earth, by making geological maps to narrow down the target sites. It's often said that we know the topography of Mars better than that of Earth because there's no ocean on Mars. And there's some truth in that. And this shows where the current and recent crop of rovers has landed on Mars or is currently working on Mars. And I'm going to talk about, where is it? Columbia Hills in particular, number 2 there. And here we are at Columbia Hills in a place called Home Plate. This is a small volcano. And it turns out that around that volcano, spectroscopically, has been discovered a lot of opaline silica. That's a common precipitate from hot springs. Same has been found here. You can see that whitish rim. Let's go closer. And one of the current crop of rovers had a technical problem and a wheel jammed, and it dragged through the sediment there and exposed this white stuff, opaline silica. And interestingly, it's possible to compare in detail the structures of the opaline silica at home plate with similar deposits in the Atacama Desert. And we're looking at in Chile, we're looking at the Atacama Desert there. And so on the left in the red patches are the knobbly features that are seen on Mars. And they have very distinctive shape, really like something we call geyserite from hot springs on Earth, which very knobbly precipitates formed in microbial mats. Well, on the right in the grey and black are features in the desert in Chile with the same structure. And there we know how they formed. There's that comparison again, 1 to 1. And if you look carefully, you can begin to see mats of filamentous organisms there. And if you look closely, there's no doubt that those structures are filamentous organisms. So now we have a 1-to-1 comparison of structures at home plate on Mars and near identical structures in the Atacama Desert, built by microbes. So it's a hot lead. And if you were going to go back to Mars to follow up on that hot lead, wouldn't you do that? Well, I would, and Martin would, and Martin's been advocating that at a recent NASA meeting in the US. But it got voted fourth in a vote. Well, voting is a strange process in science, I've got to say, but that's what they did. And there was a lot of emphasis on other environments, which are particularly deltas, where you can find a concentration of organic chemicals that relate to life. But we know from work in the Pilbara and elsewhere that is a very dangerous approach, because you can find an organic chemical, you ask yourself where it came from. Exactly the same happened on Earth. A good friend of mine who's an organic geochemist, whose name I won't mention, partly built his career on finding these biomarkers in Archean rocks on Earth, and then he decided after 20 years that they were all contaminants. And that's a very unfortunate thing to happen in your career, but he was man enough to accept the fact that that was true. So to focus on something like delta deposits and look for chemical evidence of life is dodgy. In contrast, we have the hot springs. And here on the left is a map that in black shows all the fluid flow pathways. Here you see it in the field. And there you see this network of fluid flow pathways, now we call them veins, made of chert and barite, that go up to what is now a hilltop, and partly forming that hilltop is a layer of sedimentary rocks that includes the 3.49 billion year old stromatolites. So here we have clear evidence of a hydrothermal system. It's been mapped in detail. There's the scale. And not only do we have the stromatolites, but we have isotopic evidence of life in these sediments. And so, as I described for the calderas in Yellowstone and White Island, this is what happened. At one stage, shown as stage 2 there, there was a volcano, and it blew its top, formed a huge crater, and the crater filled with water. Could have been an inlet of the sea, or it could have been salty water, fresh water, and the hot fluid flowed up these channelways and formed deposits and enabled life on the subaqueous environment, and formed a very characteristic sediment that we call geyserite, which forms only around hot springs and geysers. They're very finely laminated, originally opaline silica. Now, in this place, microcrystalline quartz. And the remarkable thing about this is the level of preservation of the original structures. The grain size, the crystal size of the geyserite is only a few microns. So it's hardly been cooked up by the Earth's heat at all, which is extremely unusual for such old rocks. And Tara Jokic, who did a lot of this work along with Martin and others, has now found a number of examples of these and can draw a one-to-one comparison with modern geysers, such as Old Faithful. So that has led to really what amounts to a new model for the origin of life. Now, we don't know when life started, but we had a lot of evidence of the way life was existing at 3.49 billion years ago, now from the Pilbara. And a few years ago on a trip that Martin and I ran to the Pilbara, we had two really creative American scientists, creative in the best sense, looking at the rocks, and they came up with this model. They already had a chemical model for the origin of life, but they weren't really able to place it in a real-world, early Archean environment. And this is it. So that they've got a caldera there and some active volcanoes in the background. They've got organic molecules coming from space. We know there are a lot of organic molecules on so-called IDPs, interplanetary dust particles, and comets and so on. So organic molecules raining down on Earth, ending up in hot pools or little lakes in the caldera, lakes that go through a wet-dry cycle and sometimes dry out and sometimes stay wet. And the original oligomers, short-chain hydrocarbons, gradually build up polymers. And by a series of chemical accidents, one of those polymers turns out to be RNA, and then the double-stranded DNA. And that leads to evolution, maybe through something like viruses, to the first cells. Now, some of that, of course, is speculative and is going to remain speculative, but it's a good model, and ultimately it will be tested, and it makes a lot of sense. And it's a model we can use in thinking about life anywhere in the universe. Now, curiously, somebody else thought of it first. Always happens. I'll let you read it. And it was Charles Darwin and his warm little pond. In a flash of inspiration, you might say, in a letter to the biologist Joseph Hooker. And it's quite a remarkable coincidence. So now I say this is my prediction, but it's the prediction of other people in this audience as well, that the evidence for former life on Mars will be found in ancient hot spring systems like those that we, that is Martin and students, have discovered in the Pilbara. And I think that could happen quite soon, maybe within a few decades, in robotic missions. But in order to be convincing, I'm convinced that we'll have to bring samples back to Earth to apply more sophisticated microanalytical techniques than can be currently at least applied in Rovers. And there are plans for sample return missions for starting in 2020 for NASA. That may happen. So, you know, if we're lucky, by 2030 we might have really intriguing evidence. But being a normal field geologist, basically, and wanting to go to an area where we find fossils, I think we're going to have boots on the ground in the end to use our intuitions to interpret what we're looking at and high-grade the sample collection process. So I think that there will be astronauts on Mars within this century anyway. And it'll be rather like what we have in Antarctica. There'll be exploration bases on Mars and science exploration bases. I don't think within the foreseeable future there will ever be colonies, so-called colonies on Mars. And I think the whole idea of colonising Mars because we're making a mess of the Earth is immoral and obscene. So despite the fact that Elon Musk has a lot of money and he can build rockets, it's not going to happen. So to finish up, just last week, Brett Beddington and Martin and Carol and myself were out in the Pilbara trying to build local support for conserving the critical areas in the region we call North Pole. And as I said at the outset, there is very strong local support. And Brett has brought along brochures that we've prepared about what we're doing, and they'll be available downstairs, I guess, Brett. And so feel free to take those. And feel free to contact us if you're interested in this project with ideas or money. We need quite a bit. But I'm very, very optimistic that this will actually happen. I've seen it happen in Shark Bay. I was involved in Shark Bay from 1977 onwards, and now that's a World Heritage Area and Marine National Park. It's happening in the Northern Flinders Ranges as we speak, and Brett and I are involved in a major conservation effort there. So we know how to do it, and I think we'll get it done. At the moment, that's what conserves one of the key fossil sites in the Pilbara, that sign. That's it. No boots on the ground. There are some really dedicated people, caretakers at a nearby inactive mine, but there's not much they can do, really. So that sign says you shouldn't be here, but you're there and it's already too late. And we know that some large samples have been taken within the last year or so and have probably been exported. It's not the only value of that area. There are lots of Aboriginal petroglyphs, such as those. And there's interesting history of the early mining. This is a gold battery where the gold ore, very small deposits of gold, by the way, where the gold ore was crushed and mixed with arsenical water to dissolve the gold, and then allowed to flow over copper plates, and the gold precipitated on the copper. So that's about 100 years old, I think. So, and then there's the flora and fauna, which is, to my eyes at least, interesting and beautiful. So there are a number of reasons for conserving this area. That's the brochure that we've prepared. You won't be able to read it, doesn't matter. But just to emphasise that you're very welcome to contact any of us if you're interested. And then just last week, as Martin told us, Tara had published in Nature Communications this whole story about hydrothermal systems at 3.49 billion years ago. And she's here. You can talk to her afterwards. Thank you.
Fantastic, Malcolm. That's a beautiful overview of a life's work and ongoing work, isn't it? So it's still a lot going on in that area. And we'd love to hear from the audience. If you've got any questions about early life on Earth or the search for life on Mars, please feel free and let us know. So, first hand up.
Hi, Malcolm. Thanks for the talk. I got a question about chemistry on Mars. Acetate, chloroform, and dichloromethane. Have they been detected? Do you know?
Tested in what sense?
Detected. In the sense that we know there's methane there.
Yeah, we know that there are alkaline salts there of the sort that could support metabolism. I think that's the best answer I could give. Brendan would be able to do better if he is willing to say something.
Well, I don't know much about the I think I know where your question's going.
Yeah.
So, I'm not exactly sure on the makeup of where dichloromethane found in Mars.
Yeah, so chloroform and dichloromethane can come from volcanoes and support what appears to be very ancient respiration on Earth. Dihalobacter and Dihalococcoides, those sorts of organisms, bacteria.
Yeah, in highly saline environments particularly. And I think it forms partly in the atmosphere, doesn't it? Anyway.
Not sure.
That's as far as I can go.
Hi. I've read that there are ice balls located on Mars. Would you be able to comment on biology on these balls in more detail? Thank you.
Did you say ice pools?
Ice poles. They are ice.
Icy poles.
Yeah.
Oh, yep, icy poles. Yes, indeed there are. And it's water ice and carbon dioxide ice. And we know that it's water ice both from spectroscopic observations and carbon dioxide ice, and also from the temperature at which it evaporates from winter to summer. And so that on Earth, I think we all know that there are microbes living in Antarctica, for example, in very cold environments, in ice-covered lakes. And it turns out that if you have enough salt in water, microbes can utilise the water down to minus 20 degrees centigrade. And that's the sort of temperature you would expect in the icy deposits on Mars in summer, for example. But then we have deeper water in the aquifers that produce those small gullies I showed a photo of. So it's entirely consistent with an environment that would support life.
I'll take Peter in the...
Thanks for a great talk, Malcolm. You mentioned Darwin's speculations on the origins of life, the very early origin. I understand he was concerned about the lack of evidence for life having emerged on multiple occasions on Earth. And I just wondered, is that still the current belief among evolutionary theorists? And if so, what implications does it have for the prospects of finding life on Mars?
Well, I'll just remind you, you're talking to a geologist and a paleontologist first, not an evolutionary theorist. We really don't know anything about the potential first billion years of life on Earth. So we can only speculate. Life might have arisen many times. And it's often said that most or all of life would have been wiped out by the so-called last heavy bombardment at about 4 billion years ago by incoming asteroids. But in fact, that seems unlikely because we now know that life can exist probably down to 10 kilometres in the crust. So while there may be a filter there that would wipe out mesophiles and things living at what we call ambient temperature, and only hypothermophiles or mesophiles got through that filter at about 4 billion years, but that's all we know.
Thank you.
Thank you, Malcolm. I'm glad I'm talking to a geologist. I have a technical question. I haven't heard very much about the dating of the surface of Mars and the dating of the formation of those water gullies, and the dating of how long ago the temperature on Mars was warm enough for there to be water and so on. We know quite a lot about the dates at which life evolved on Earth, which life formed, and you mentioned 3.49 billion. What do we know, and can we correlate anything date-wise between what happened on Earth and what happened on Mars? Have we dated anything?
No, we haven't dated anything except a few meteorites that have come from Mars and landed here. And then they're around 4.4 to 4.5 billion years old, like other meteorites. So they date from early in the solar system. But we have a crude clock that is used to date geomorphic surfaces on Mars. And that is the so-called crater density, the number of impact craters. And we calibrate that clock by looking at the impact history of the Moon. And you remember that if you look at the Moon, it's very heavily cratered, and the samples that have been dated, mostly from the rocks brought back by the Apollo astronauts, have dates that peak around 4 billion years ago, suggesting that the major impacts on the Moon happened about 4 billion years ago. So by comparison, that would have been the same on the Earth. But there's quite a bit of doubt these days about the validity of that whole clock, because it's contended by some people at least that it's a very biased sample set that was dated from the Moon, and that most of the samples in fact came from one major impact event, which just happened to spread over a large part of the Moon, and that just happened to be where the astronauts sampled. So there's quite a bit of concern about the validity of that dating technique anyway. So we only have a very crude clock, but it seems reasonable to say that what we're looking at on Mars in terms of the crater terrain and near the equator in the south is older than 3 billion years.
Okay. What would it take? There will be future missions to Mars, I'm sure. What would it take? What would we have to put on Mars in order to be able to do some dating?
It'd be much better if we brought the samples back and dated them here, because we can use much more sensitive instruments here. But I think the first thing to do is to go back to the Moon and do a more careful sampling of the rocks on the Moon to better calibrate that clock that we're already using. So I would go back to the Moon.
Thank you. Thanks. The evidence you showed for the liquid water and those delta systems is fascinating. That would be presumably a very interesting area to investigate for future missions. The possibility of the very high brine contents of that water. But also I wanted to say the evidence you talked about for the isotopic abundance in methane of deuterium and hydrogen, what does that indicate, or what will that indicate for the likelihood of life? And could that be applied to specific areas, such as those delta systems?
Well, yes, it could be applied to those areas. But it suffers from the difficulty I mentioned, and that is they can find these hydrocarbon molecules, but you can't be certain where they came from. And there are such molecules in space anyway, and they can form through hydrothermal and other processes on a planet in addition. Mm-hmm. So it's a bit of a dead-end approach in my view. But those sorts of isotopic measurements are very useful in learning more about the metabolisms of ancient life on Earth, mm-hmm. and they would be on Mars as well, if we could definitively say where they came from. Okay. But we can't.
Okay, thank you.
Okay.
Thank you.
Okay, well, I think we'll wrap it up there, and if you'd just like to join me once more, and thank you, Malcolm, very much. And,